rocks around Nature's Valley. And that's the scene that you recognize from where we were this morning. And we'll go through a short version, which I'll read mostly because otherwise I'm going to forget it. We'll talk about the location, where they actually sit relative to the coastline, what they're made up of, these two main rock groups, roughly, very briefly, geological ages, and where it fits within South African stratigraphy. Then we'll come to our place. We've got the Tsitsikamma Terrace, sea level change, not climate change. And then what we see, what we saw today at Blue Rocks, and then what you see at Salt River, what Nature's Valley looked like during that Holocene period. I identified here as 4,000 to 5,000 years ago. Now, you know how little that is on our time scale. You know, we're now down in the millimeters. And what Nature's Valley geology looks like today. And then another one I've just tucked in here called Who Was Here Before Us? So I hope we can cover those things today. So that was the first question, I think, when I've been here 45 years. Beefy Mance, who used to own the shop here, he said, "What's to see at Blue Rocks?" Well, it took me 40 odd years to get around to writing something. So, but that is a question that many visitors and residents ask. You know, whether you're relaxing or walking around, stubbing your toe, cutting your foot. And the geological history goes back to the early stages of deposition of the Cape supergroup about 500 million years ago. And the subsequent building of the Cape Fold Mountains in the period about 280 to 345 million years ago, or 235 million years ago. The rocks represent the seafloor of the ancient, now extinct Agulhas Sea. Deposition was in estuaries and shallow marine environment at or below sea level. By the end of this active sea, they were buried to at least 4,000 to 5,000 meters below sea level. Mountain building raised these rocks up above sea level to the heights of the Himalayas and the Alps. When the Agulhas Sea was compressed closed, the supercontinent of Gondwana was being assembled. We talk about continents being assembled and splitting apart. The breakup of Gondwana lowered sections of the continental margin along the southern and western Cape coastline back below sea level, about 135 million years ago. Continental uplift over the next 60 million years led to erosion of the land and incision of at least two major store stands of sea level between 5 and 24 million, visible as terraces on the modern landscape, the Tsitsikamma platform, and led to down-cutting of the Crotrophia, Blowkrans, and others as sea level dropped even further to 130 meters below current sea level at the outer edge of the Agulhas Bank, some 70 kilometers offshore Nature's Valley, about 20,000 years ago. So this is the scale of geological time. As I mentioned out the rocks there, things are not like on, off, on, off, on, off. They backwards, forwards, up, down, upwards, forwards. So all we're able to record is the last evidence of what has happened. So in subsequent sea level to at least 8 meters above current sea level led to erosion of identifiable wave-cut notches at the point and on Blue Rocks. And a Holocene high stand sea level 4,000 to 5,000 years ago eroded the area now known as Nature's Valley and provided space for deposition of sand dunes, leading to the present distribution of cliff sand dunes and river terraces. So that's the short version. But maybe gives you some idea of kind of the scope of things. So the most prominent things leading out of here is as you come up the Crotrophia, you're onto this relatively flat surface, got rivers cut into it. You've got this high mountain range to the north, which has got Formosa at about 1675 meters, and these precipitous cliffs to the south. And this level plain in between, which as I described briefly out there was in fact in two levels, the Miocene and the Pliocene terraces. This all started with the deposition of the Cape supergroup, which was an extensional subsiding trough and never opened to be a fully fledged ocean as like the Atlantic. There were no mafic basaltic rocks intruded, and it was stalled. It was like a failed ocean basin. But it was enough to build nearly 10,000 meters of sediments from the Table Mountain Group through to the Bokkeveld Group, through to the Wittenberg Group, into the slowly subsiding sea. You'll see on the image, you've got Falkland Islands to the south, Antarctica to the east, and Africa in the middle, and South America to the west. And this Agulhas Sea covered those things. The northern edge of the Falkland Islands was in fact up somewhere near Natal. So we're going through the fundamental stages of plate tectonics. This is stage 2. We've got deposition, slowly widening ocean. Now, the scale is almost irrelevant. It's really a cartoon. But to the south, we had the Falkland Islands block, and the Paleo-Pacific Ocean was out that way. Don't forget things that moved around. They were pulling apart, and all the rocks of the Cape Supergroup were deposited in the slowly subsiding sea. Things changed around, and it didn't happen like that. There was probably a lot of stop-starts and all the rest of it. But eventually, the Paleo-Pacific was obviously stronger and started with a subduction zone under the Falkland Islands and what is now South America, and that pushed the Falkland Islands into this basin. And we had the development of this massive mountain range, which has been estimated to have been up 8,000 meters, because that seems to be from the people who study it, that's like a maximum limit that mountains can get to before they're eroding faster than they could go up. And you can see there, I've put a dashed line in where the current coastline would have broken away when the whole thing turned around. And what you see here is what they call a subduction zone, where the Pacific plate was pushing underneath the Falkland Islands. Sorry, and what you do see on the left there is, in fact, as this mountain range was building up, the inland was being depressed, and that was the start of the Karoo Sea. So at the end of the Cape Fold Belt, the Karoo Sea and the Karoo rocks were starting to be deposited. What you see now is this really quite simplified but very complex series of folds and thrusts being rocks pushed on top of each other from south to north, and on the Cederberg side from west to east. And that defines what we have, the Cape Fold Belt. And then what's also evidenced here, you've got the Great Karoo on the left. In the middle you've got the Oudtshoorn Basin, and on the right you've got the current coastline. And that Oudtshoorn Basin is also a reflection of the separation of Gondwana land, that things pulled apart, and these younger basins separated. And when you get these piles of conglomerates that somebody mentioned, you see coming down into Curbom's Valley, and that was a new ocean starting to invade the land, and the rocks are falling in and being churned around in this what they call a pebble mill. So currently the Cape Fold Belt forms a prominent east-west linear belt across the southern part of South Africa. Was originally about 1,200 meters long, and currently still extended 400 kilometers inland. It's been identified in boreholes near Beaufort West, drilling for oil. They've identified they go through the Karoo into Cape Supergroup rock. It was deposited in relatively shallow marine environment, similar to, and is exposed, that's all exposed in the Cape Fold Belt today. So to the north you had these ancient mountains, granite terrains at the center of the core of South Africa, older quartzites and sandstones, and those rivers were washing down into this subsiding basin. But what did it look like? The Table Mountain Group, the base of which is the base of the Cape Supergroup is the Table Mountain Group. It's been called by John Compton at UCT as a huge pile of sand, which it largely is. But how does that deposit like that? Back then, 500 to 600 million years ago, the Earth didn't look like it does now. It was quite flat, boring, and Gondwanaland was situated somewhere around 60 degrees south, subpolar latitudes. It was cold, it was windy, there was no vegetation. The only thing that probably grew was moss, lichen, algae, things that survive in those environments. Lichen, as you know, is probably the most hardest things to get rid of. You don't want to get rid of them. So the image on the left is actually an image from Iceland, which shows the type of deposition environment, these broad, braided river channels, swept by icy wind, and as you'll probably find in Iceland, algae and mosses and sedges and things. On the right, the sandy beach at Nature's Valley is probably what it was, but there was just no greenery. The type of river was like that, just meandered into the sea and was depositing sand. This is just an example of the names we give to piles of rocks. In this area we have the Peninsula Formation, which is just largely these white quartzitic sands. Then halfway up that, at about 440 million years ago, this ice age developed into a full-on ice age. It's been called the Ordovician Ice Age. And we see it represented here in what is known as the Bokkeveld Formation. It is a horizon of pebbly sandstones, drop stones, faceted pebbles, and that proceeds into the Cederberg Shale, which is the outwash of fine-grained material from this glacially eroded surface, where the rock had been ground up and all this fine sediment was washed into the sea. So you had icebergs floating off the ice shelf, dropping pebbles in the mud, and they found lots of evidence of that, and particularly up in the Cederberg. There's even evidence where glaciers have overridden the underlying Table Mountain sandstone and folded it. So it was still a very active, dynamic environment. It was in the Cederberg Shale that some of the really earliest signs of life, as we like to think of it, things that move around, started to appear. Trilobites, those big lights-like looking things that we've seen in the Bokkeveld and the Cederberg Shale. And that's quite a consistent, really soft, shaly, mudstony sequence throughout the whole belt. And in fact, is the only reason why it's able to map the Cape Fold Belt from aerial photographs, satellite photographs, because it's a very distinctive, usually weathers at a smooth green surface in all this white and grey rocky landscape. So there's an example just of how that glacial horizon, those glaciogenic rocks. So we had a number of fossils in there, brachiopods, which are like little shells, and trilobites, and you see various trace fossils. Trace fossils are where you've got evidence of a thing with legs having crawled across the sandy or muddy shoreline. That's the major Ordovician Ice Age, which some recently has been published that it was caused, that the existing cold conditions were just flash frozen by a shading event, by an asteroid near impact on Earth. They found evidence of that age of asteroid impact in many places. They reckon that the sky was full of dust and cooled everything right down below freezing. So then we came out of that into this rather quiescent sea after another sandy period, the Bokkeveld Group, and this is the group that we see here. The lowermost unit, the Guido Formation, which is a very dark, muddy, sometimes stagnant, little stagnant pools in which pyrite and iron sulfide developed. But else places, it's sandy, and you get the further proliferation of all these early sea creatures. You see crinoids, which are those long sort of branching stems of early corals. And in that environment, the seas were warming up and life exploded. So in that sequence then, we're really only looking at the Agulha, which is at the bottom. The other shale formations and sandstones are really beautifully represented in the Cederberg, as you drive from Ceres up towards to the north. Up that valley you see beautifully layered sandstones and shales, which is the type area of the Bokkeveld. So where are we sitting in this? On the left is the sort of standardized geological timescale, and we're just talking about two fractions of that. On the right is a representation of all the layers of the stratigraphy in South Africa, starting from basement granites at the base, going up through the Table Mountain Group, Bokkeveld Group, Witteberg Group, and then into the Karoo, and topping off with the Bredasdorp Group, which is younger than 1 million years, and those are all the cemented sand dunes along the southern Cape Coast, in which has now been found evidence of early man. So what did it look like around here? Well, it looked like exactly as it does now, but it's interesting that this image I found in the breakwater lodge at the V&A waterfront one day, and it shows an early traveller's representation. So this landscape made an impression on people from an early stage and represents that Miocene terrace. But interestingly, their map making was a little bit out. They have all the rivers inland flowing west, whereas now we know those ones flow east. So you come to what it looks like today. That's a section of the current geological map of South Africa, of the Oudtshoorn block. And I've just clipped out this. You can see there the Bay of Nature's Valley. I've highlighted the Miocene sea cliff on the dotted line, where suddenly you can see the contours all change. It's very steep. I've highlighted the N2. You can see the Kruitrivier and the Salt River I've highlighted there. Interesting, the Salt River is a young river, as is the Miocene River to the west. They only flow in the mountains just above the Miocene sea cliff. But they still have cut down very dramatically. You've got the fault there that defines the point, the Kruitrivier fault. On the right-hand side, a little photograph of a waterfall on that Miocene sea cliff, and that's that's a favourite walk for people from here on the early part of the Tsitsikamma Trail. It's a nice stopping point. So if you took a cross-section across that yellow line AB, this is what it would look like. And I'd say stylized, but not really. It is really flat. It is really flat. And you do see that when you drive up out of Nature's Valley towards the crags. You'll see that flat surface leading up to the mountains there. And incised into that, there's the Kruitrivier along the Kruitrivier fault, the Sotrivier, and then you drop down onto the Pliocene coastal terraces. This is a section from Kierboomstrand up to Formosa. And we have there just a reminder of the ages of those terraces. So what causes marine terrace formation? You have sea level change due to ice ages, and you can have isostatic rebound. When continents are pulled apart, the continents rise up and they are floating in the denser mantle. And a combination of both. You get this change from isostatic rebound to eustatic changes. So isostatic is movement of the content, eustatic is movement of sea level. This representation of sea level relative to what it is now, the sea level was never at 300 meters above us, but relatively it was 300 meters higher. during the breakup of Gondwana, because everything was depressed down below sea level. And through that time, you can see two major ice ages, the Bokkeveld and then the Agulhas, which is the basin of Karoo. And then coming into the eustatic sea level change, lots of up and down motions of sea level due to freezing and thawing of various major and minor ice ages. So as I said, the pre-Gondwana major ice ages have been ascribed to either shading of the Earth from asteroid impact or volcanic activity, which led to mass extinctions of early life. In the middle of the Karoo is an evidence of that. The Permian-Triassic boundary is a major extinction there. Bruce Rubich at Craft will tell you a great story about that. Or the explosion of carbon dioxide, explosion of light consuming carbon dioxide, and thus reducing the greenhouse effect. So you go from heated up in a greenhouse to freezing cold when you get rid of the carbon dioxide. But what do we see here? These three significant levels. And you see them quite nicely from blue rocks. You've got the Miocene Sitsikama terrace at about 150 meters near the coast, going up, sloping up to 300 meters. But don't forget, as you see waves running in the shore, they don't run in like that, they run up the beach. So on an eroding coastline, they erode up. And this is not like we're going up to there, then we're coming back here. Over the millions of years, chop, 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 and that's called the buzzsaw effect on these surfaces that enables the sea to break the rocks, roll them around, and give them all these beautiful pebbles that you can see. If you walk up from Salt River to the top of the pass, from the Kalunda Kloof, you see certain clusters of pebbles in the fynbos there. And at Pebble Beach, all those lovely pebbles down there have probably fallen down off that surface. They've been reworked and remilled during the Holocene and currently. The Pliocene was somewhat minor, but we have a beautiful relic representation in the pig's head. So that's the Miocene is level B, the Pliocene is level A, and the Holocene surface, which was 4,000 to 5,000 years ago, is blue rocks, those three main levels. Undoubtedly, if anyone would apply whatever technology is available to really date very precisely, but that's as it is now. So when you drive up to the pass on the east side and you look back towards the west, you see that Miocene terrace, very level across the Croix-Riviere. At the top of the pass, the sandstone rocks are very white and soft, and that's also an indication that surface has been weathered and exposed to erosion for a long time. So very soft and weathered. So the weathering went down quite far. But then I think quite spectacularly on the top of Pig's Head, and I'm sure most people have been up there, delicately, there's a beautifully preserved remnant of that Pliocene terrace. So you've got lovely rounded pebbles, somewhat smaller, and they cemented in sand in the top of that terrace, which is quite unique. And for whatever reason, Pig's Peak is there. A lot of silicification related to the Croix-Riviere fault. It's an amazing preserved surface. So then we come down to sea level again. And how do we recognize these surfaces? Well, if you look back from up the road towards the Sandparks camp, you can see quite clearly the Pliocene terrace. It's that beautiful sloping. You can see the slope on it. And then if you look down close to the bottom of the point, there's sort of a single level that covers the last outcropping rocks above sea level, and then you can extend that back into those really rough rocks on the east side of the Croix-Riviere estuary. And those extend, and you can find evidence that they extended up that valley in conglomerates and sandbars in the side of the road. And those conglomerates resulted from higher levels of sea level. At that time, when that was a much wider estuary, and sea level was probably coming right into it. On a broader picture, we have the Paleo-Agulhas Plain. This was the Pleistocene shoreline 140,000 years ago, and then again 20,000 years ago, 130 meters below sea level. That outside grey wedge has been mapped and logged in a lot of detail by the Council of Geoscience. There's some magnificent work published on it where they identified various shorelines and identified where early people could have lived. Because as you get to the current coastline, the Pinnacle Point, Blombos, the Kelders, and east of here as well, there is evidence of human habitation of this coastline 90,000 years ago, 70,000 years ago. And they can identify that from the remains of animals and pollen spores that they find in these caves, that there was a landscape out there which was browsed by large herbivores. There's even evidence there might have been elephants, certainly giraffes, and large long-horned buffalo and stuff like that. So this was a living terrain. The climate would have been different. It would have been really cold. So it wouldn't even have been fainals, but there might have been sedges and grasses and so, and quite wet, swampy. So if we're going to talk about sea level change, there's this paradigm that sea level change is a certain consequence of global warming, and we know that people have been involved with that. But ice age cycles for the last 900,000 years have seen sea level fluctuations between minus 130 meters and plus 8 meters. Present meltback of all remaining ice on Earth will create between 58 and 65 meters of sea level rise. This is unlikely to occur, as the last time this was in the late Cretaceous, 65 million years ago, when continental configurations, plate tectonics, were different and ocean currents, wind systems were not set in place. And the Milankovitch cycles, which we'll come to next, were also not established in the universe around us. So they're based on past fluctuations from a geological perspective. In the next 200 years, global sea level could be expected to rise as much as 1 to 1.8 meters, and 11 meters in the next 40,000 years. This is a natural process, and although human impact may enhance or accelerate the rate of rise, climate change and sea level change is natural. And the work done by Haley Corthray at the Council for Geoscience, and there's a magnificent series of papers in the Quaternary Science Reviews. So what are the Milankovitch cycles? Basically orbital cycles, the change in the shape of the Earth's orbit. It's not circular, it's oval. It's an oval, and that oval rotates. So that's the precession. You have the precession of the Earth's axis, changes its axial angle. It's not that it doesn't, it rotates like a topspin. Four different periods of changes of Earth's rotation, and that various combinations of these can, in fact, if they're all on the worst side of cold, that could really be instigating a major ice age period. So now we finally get to what's under our feet. Geologists tend to rattle on a bit about what's around them, so bear with me. We stood there on exactly that spot. We observed those old marine erosional surfaces up at the Miocene, the Pliocene, the Holocene, and the current erosional terrace that we saw being etched. So here's try and explain what I did there. How these rocks that were originally flat-lying mudstones get to be sharp, jagged, and pointy by a compression, folding, and the formation of what's called a cleavage, which is a splitting direction where all the platy minerals, the clays, are becoming turned to micas, and they're all aligned parallel to the foliation, the axial plane of folds. Folds like this, they have a central line which is called the axial plane. The only place you can see where there's real differences where you have a sharp angle between those cleavages and bedding. And on the track to Salt River, you come across that as you come around the path, you go down through the dip, jumping the waves, it's difficult at high tide. But as you come up the other side, you see this clear band that dips slightly to the north. It's quite iron rich as well, which explains some of the iron rich pods in the sediments that we saw at Blue Rocks. And there you can clearly see the high angle of the cleavage to the bedding. When you get up on the top at the Nature's Valley outlook, you can look down on Blue Rocks, and I've sketched in there what I believe to be fault outlines that form Sinker Bay and the limits of the Blue Rocks outcrops to the east, and then Kruitrivier on the other side of the bay. And the age of these southeast trending faults may relate to the breakup of Gondwana land, similar to those bounding the oil and gas bearing sedimentary basins between Cape Agulhas and Port Elizabeth. They form these wedge-shaped basins which are filled with younger sediments as a result of Gondwana separation. So what's at Salt River? Well, there I think is a lovely evidence of a drowned river valley and how it would have cut down from the other level. Although the Salt River is a relatively young river, rising just above the Miocene terrace in the mountains behind that, it cut down through the Miocene and Pliocene terraces and was obviously flowing out onto the Paleo-Agulhas plain. And that Salt River, it cuts this beautiful valley, which also, the embayment there partly formed by a fault that runs across it, is approximately the same orientation as those at Blue Rocks. And as you come down the path from Salt River, from Pebble Beach there, those rather dodgy steps, there's lots of brecciated and iron-stained rocks there which sort of define that fault zone. So during the Holocene high stand, which really gave rise to Nature's Valley, sea level was such that it cut into these predominantly softer shale rocks of the Gado Shale, which formed from just west of Salt River all the way around to the Kruitrivier. And particularly from Blue Rocks up the Kruitrivier, it was obviously where it really had greatest effect, because the Kruitrivier fault formed the boundary there, and the river the sea could rush in and carve out the shales. So it cut back as far as the current cliff edge behind the valley, and we see remnants and conglomerates in the bottom of Kruitrivier Pass and along the road to the campsite. This is along the road to the campsite. On the left there you see a beach sand, two ages of beach sand. One is very white, and it was obviously must have been weathered when the one on above was being deposited. And then these conglomerates, these pebbles that are suspended in a rather unsorted fashion. These could have been talus slopes running down into this C4. Sure. So during the high stand, that's what the geology looked like. You had the sea rushed into that purple line. It was eroding at that surface. Probably extended all the way up the Kruitrivier. I would say probably at least as far as the Kruit-Bobbejaan intersection. You had the terraces. You had the Pig's Head Miocene terrace on the right. You had the Holocene high stand terrace of Blue Rocks. The Nature's Valley embayment, and then those white lines are paleo and current stream values. I believe that, or they're current, and I believe they were flowing back in Holocene time down that same trend. Back in 2008, the municipality commissioned a study from Ninham Shand engineers to look at alternatives for sewage disposal in Nature's Valley, which is always an ongoing issue. Up until that stage, everything was always by septic tank and French drain soakaway. Most times worked perfectly, but there was a bit of an outbreak about then of E. coli in the river, in the lagoon and so on. And this study identified a band of clay at the back of the village up against the mountainside. And it seems that septic tank discharges from some properties there were not being soaked away, but in running down across the clay into the drainage and then down into the lagoon. Elsewhere, it's very sandy, and the fossil sand dunes outlined in yellow, and that's never been a problem with soakaway. So the section line across there just gives you some idea of the profiles. You can see the clay level is at what seems to be the same level as the Holocene high stand. There's a ridge of shale on the seaside of that, and that bounds that clay-rich area. The boreholes that they drilled were not very deep, but they did serve to identify the position of that clay. And in the middle is a fossil dune, a complex fossil dune. You basically have got the intersection there on the left, St. George's and St. Andrews, and on the right, a deep trough there before the recent and modern dunes is in fact St. Michael Valley. In between is the fossil dune up to 10 meters high. And it's in the cuttings through that where this Bokkeveld shale has been used to support the wall. So currently, that's what we have. We have preserved the remnants of the Holocene high stand in the shape of the valley outline. We've got remnants of the Pliocene terrace at Pig's Head. We've got conglomerate remnants at the base of Grootrivier Pass and along the road to the Sandparks camp. We've got the shale ridge down the middle of the valley, which in fact there are a couple of houses, mine being one, and our neighbours where they were intersected in the foundation, so they are there. So there may be two levels, the upper Holocene high stand and the lower one, which is cut it a bit lower, which we don't see now. We've got the paleo and current rivers, which basically run where they are now, and then the modern beach and dune cordon. That's what it is now. So who was here before? Because we know that along this coastline, 350 kilometers of coastline, this group, the Southern Cape Coast Tectonic Project, led by Charles Helm, a South African out of Vancouver in British Columbia, are working in identifying these vertebrate track sites. And strangely enough, 350 track sites identified along that coastline. In these particularly cemented aeolanites, these are now the dune sands, part of the Bredasdorp group, less than 1 million years old. They've been cemented by their contained shell composition, dissolved by rainwater, and then re-cemented. And in that they find not so much impressions in the ground, but usually on the ceilings of rockfalls and caves, preserved there. If they're on the ground, they generally get more easily weathered away. So that Pleistocene epoch ran from 2.6 million years to 11,700 years. That was now the Holocene era. And one discovery in the Garden Ridge National Park has been identified as the oldest Homo sapiens footprint anywhere in the world, dated back 153,000 years. How do they know that? Well, they use a technique called optically stimulated luminescence, where grains of sand that are exposed but have been sheltered, they can determine from trace amounts of elements in them when they last saw light. And it's quite new, but it's absolutely crucial for this type of study. As I say, usually discovered on the ceilings of caves and rockfalls as negative impressions. I sent to Rudy a link of a paper written on that, so if you want a copy of that, ask him. It'll be very interesting reading. So during this period, Earth was in a long cold phase, from 195 to 125,000 years, but there's evidence of human habitation along the southern Cape Coast since 164,000 years ago. At Pinnacle Point, Mossel Bay, from 164 to 90,000 years it was occupied, then became sand-filled, maybe because sea level dropped again and they were going out further to find food, and then was reopened about 40,000 years ago. And it's a magnificent place to go to. Unfortunately, you can't see very much because to protect it from fossil hunters, etc., they had to sandbag it. But they left some of the crucial items, and there's a very illuminating display. And that's Pinnacle Point below the resort and golf course. Further close to us, there's Classes River at Humansdorp, which is occupied from 125 to 48,000 years, and then Mikey's River, just down the coast here, which is occupation from 10,300 to 1,000 years ago, and there's the remains of 100 children. Cape Nature taken custody of that, so they will have more on that. So that's how sea level goes. It comes down in a series of steps during the ice age and then shoots up quite rapidly. So, right here on our doorstep, we've got a little mystery. We've got the Pig's Head Midden. Those of you who've climbed up to Pig's Head, the first 20 meters or stuff, in fact, right on the road to the Kalunda hut, there's a massive pile of shells. And this extends at least 20 meters up to the base of Pig's Head and presumably down below to the beach level of about 5 meters. So I would suggest it was possibly actively occupied during the Holocene high stand. Sea level would have been a bit higher. It was probably breaking around the rocks at Pig's Head, so it wasn't a long walk on a sandy beach to get your food. And they certainly ate a lot of it, and they reckon that's also part of the reason that the human brain developed so fast, because of all the shellfish and seafood they ate. Well, here's one other question for you. So at the base of Pig's Head, there is this rock outface which looks in part like a fire's been built there. Some of them might be more recent. Because don't forget, these are the places were occupied even by the sand and the koi and so on in far more recent time. Mikey's River was definitely occupied by the koi. So that may have been where they sheltered, maybe protected from the northwest rain, and be able to get down to the rocks to get food. But then the next photograph is not very good, but the best one I could find from my own collection. What's with that cave below the point? Has anybody ever been in there or know anything about it? You've been in there? And what's in there?
Bats.
Right, bats. No, I mean, is it guano? Is it shells? Shells. Okay. Now that's hell of interesting, because that's quite high up, and it would have been quite a tricky place for people to live regularly and get down to the sea. But maybe it was occupied at a time when sea level was higher. Get some student who wants to work on archaeology, I think there's a real story here. So I think that's it.